is lesson 5-1, relating graphs to events. Now you can use a graph to show the relationship between two variables. For example, you can use a graph to show how a quantity changes over time. The graph we have to the left here, a day's commute, shows a trip from home to school and back. The trip involves walking and getting a ride from a neighbor. We're going to label each section of the graph so that people can understand what we're doing. Please note a couple of things. First thing, time here is on the horizontal axis. Distance from home is on the vertical axis. We should always label our axes. There's also a title for the graph. You should always put a title on all graphs so that people can understand what they are. We're going to label this. Remember, we're walking and getting a ride to school and home. So that's why our distance from home starts at 0 and it ends at 0 because we started at home, which was 0 feet from home, and we ended back at home, which is also 0 feet from home. All right, so what we have here is, here's my walking part, which is probably the same over here, but we'll talk about that later. We're walking. Notice here we have several flat spaces, 2 short ones and a very long flat space. During those flat spaces, you can see that time is continuing to go on because time is increasing this way, but my distance is not increasing at all. If time is going on but distance is not increasing, I obviously am not walking or driving any further from home, so I must be still, either standing still or waiting for something. In this case, I'm going to say that at this first place, I'm waiting for my ride. I get my ride, and then this portion right here, you'll notice, is a little bit steeper than the first portion here. Because when you get in a car, you should be traveling a bit faster than when you're walking. So this would be my ride in the car. Okay. Up here, this other longer, flatter section, since it's a long time where we're not going anywhere, but time is continuing to march on, and since I'm supposed to be going to school, I could assume then that this is the time where we're at school. At school learning, time is continuing to go on, but your distance from home is not increasing or decreasing. Okay. Here, again, I'm taking a ride from the neighbor, and as you can see, it's a bit steeper. No, we're not going down a hill. If we were, that would work. But let's just say that on the way to school, they drove through town, and the way home from school, they drove on the freeway, which means freeway's a little faster, which means your distance goes by a little quicker, so you spend less time going more distance. Another flat section, maybe I'm getting out of the car, and I have to get all the stuff out of the back of the car, and maybe I had to chit-chat with the driver for a few minutes. And then last but not least here, I'm walking home. We've labeled the sections of the graph which pertain to this particular graph. Now notice, in this example, distance, which was on the vertical axis, depended upon time. The longer I was walking, the further I got from home. The longer I was driving, the further I got from home. Okay? So, distance, okay, which is on the vertical axis, depended upon the time, which was on the horizontal axis. When one quantity depends upon another quantity, always show the dependent quantity on the vertical axis. Distance was dependent, it was shown on the vertical axis. Let's look at another graph. We're describing a walk in the neighborhood. Now notice, this graph differs from the last graph just a little bit. You'll notice it doesn't go back down here to 0. That's because instead of distance from home, this is total distance. Which means by the time I walk in my neighborhood and then stop walking in my neighborhood, my distance never goes back to 0 because I'm not going away from home and coming back home. I'm just talking about the total distance I'm walking. Even if I walked in a circle and came back home, hopefully my total distance wasn't 0. Just because you ended up where you started doesn't mean you walked no feet. Right? For runners who run around the track, that would be really, really terrible. Yes, I ran 12 times around the track and went 0 miles. Not really. Okay, so let's label each section of this graph. Okay. So here we have this section here. I'm going to say I'm just taking off on a nice leisurely walk. I've got another flat section again where time is marching on, but total distance is not changing. So maybe I stopped to take some pictures or stopped to talk to a neighbor. I'm going to say I talked to the neighbor. And normally you don't talk and walk unless they're walking with you. Okay. Here, notice this is a little bit brisker than the last one, so maybe it's a little faster of a walk. Okay? It's a fast walk. decided I want to get someplace. Okay, here's my second flat section. Maybe I stop to watch the sunset. I stop to watch the sunset, and then I'm taking a nice leisurely walk home. So this is my slower walk. Because you can tell that this is not quite as steep as this, so I can't be going as fast because it's taking me more time to go more distance. Okay, so my total distance from home ends up here in what people call cyberspace. It ends, it doesn't come back down to the x-axis because it's not distance from home, it's total distance traveled, which means all I'm doing is saying for the longer I'm out, I'm just increasing my distance. Now, this last graph here that we're going to do, we're going to sketch the graph of the altitude of a pelican taking off from shore, diving into the water to catch a fish. And we have to label each section, which means we also have to label the axes and title our graph. Okay? Since his altitude of Mr. Pelican does depend upon how long he's been flying, because he's not going to be spontaneously 500 feet above the air. He has to actually get to an altitude. Time is going to be on my x-axis. And altitude is going to be on my y-axis. And of course, I should have 0 here. All right, now like I said, a pelican's not like a helicopter, it can't go straight up, so his altitude is going to increase gradually as he starts to fly. He also isn't going to fly a couple of 100 feet above the water because pelican's eyesight's good, but not that good. And a pelican is a big, bulky bird, so trying to fly that high is going to be rather difficult, and it's going to be really hard to see a fish. So he's going to go up gradually, maybe 30 feet above the water, not even maybe that, and then he's going to fly for a while, searching for a fish. So he's going to stay at that altitude. It's basically like a plane staying at the cruising altitude. This is the pelican's cruising altitude. He's going to stay at this cruising altitude. When he spies a fish, he's going to dive for that fish. He's not going to take a nice slow glancing down to the water. He wants the fish. He's hungry. So he's going to dive down quick, catch his fish. So this is what we have the part here where he is taking off. This flat portion here, searching for his fish. This portion here, diving for fish. And the last thing we have to do is we have to give our graph a title. In this case, since it was a pelican searching for a fish, I'm just going to call it a pelican searching for a fish. And there you have it. A nice, easy graph that describes what is happening. You can use graphs quite nicely for describing what is happening, especially if you label each section of the graph, so people know what's going on. Yeah.